So we've now seen that many simple materials have phase diagrams that are qualitatively similar to each other. There's a liquid phase, there's a solid phase, and there's a gas phase. And which of these phases that occur depends on the temperature and the pressure, although the precise numerical values depends quite a lot on the material. So now we want to ask why. We want to understand what is it about these materials that make their phase behavior so different. And the answer to this shouldn't be that surprising to you. The answer has to do with the molecules that make up the materials. The molecules in these different materials have interactions with each other, and what we now want to show you is that it's these interactions and their different natures that lead to the different phase behaviors. So now a simple way to show you this is just to place on the phase diagram that we've shown you before. Here's the phase diagram of water. And on this, what I've done is I've placed a sketch of what the molecular structure of the solid, liquid, and gas phase look like. The solid phase is very ordered. The atoms are sort of arranged in some sort of a lattice. It's not exactly the lattice that I've drawn here, but it's just to give you the flavor that it's a very ordered structure, which is very rigid. The liquid phase, in contrast, has the atoms in a rather disordered configuration. They're not ordered. They can sort of slide around each other, as we will see, but it has a density of atoms that is really comparable to that of the solid phase. Whereas the gas phase, the molecules are everywhere. They're just everywhere. They're far apart. They're no longer close. And these are the three mental pictures you should have in your head when you think of a solid, liquid, and a gas. To sort of test your thinking in this, I want to now give you a bit of a quiz. So what I'm going to do is I'm going to show you 3 movies. These movies are molecular simulations of the behavior of a solid, liquid, and a gas. They're simulations of water. And I'm going to play the simulation and then ask you to tell yourself, is this behavior that you're looking at that of a solid, liquid, or gas? So here's the first simulation. What you see is the molecules, and we're now going to turn it on, and the molecules start whizzing around all over the place. They're no longer condensed in a condensed phase. They're whizzing all around the jar. So what phase is that? It's a gas. The molecules are all over the place. So now, with that, let me show you a second simulation. And so this simulation I'm going to, again, just turn on. And what you see here now is that the molecules are in a condensed state. They're not whizzing all over the jar, but they're still moving by each other. They're not fixed in space. They're sort of moving, all around. What phase is that? It's a liquid. The final simulation is here, and this one should be clear to you. When we turn this one on, the temperature is much lower. And now, actually, what happens is that the molecules sit, and instead of moving by each other, they literally just vibrate like this. What is that? That's a solid. So in these simulations, which are actually a pretty accurate picture, give a pretty accurate picture of what is going on in the molecular behavior of a solid, liquid, and gas, at least of simple materials. These simulations don't actually apply for reasons that we will see to an egg, where something very different is going on. But in simple materials, what you see is even in the solid phase, the molecules are sort of jiggling. They're not actually staying perfectly still. Whereas in the gas phase, they're whizzing around like mad. And this basically shows the 2 basic ingredients that are going on to determine the phase behavior of a material, which is, on one hand, the molecules interact with each other. They stick to each other in some fashion, whereas on the other hand, molecules have motion and they like to move around. And it's really the competition between the molecules moving around on one hand and sticking to each other on the other that leads to the phase behavior of simple materials. So if we think about this qualitatively, you can also start to get some insight into the pressure dependence that we discussed before. If you take a material and you squeeze on it, then actually it's harder for the molecules to come apart. So you can see that if you're a gas, if you squeeze on a gas, then it actually wants to be, the molecules become closer together. And if you squeeze enough, a gas will become a liquid. If you look back at the phase diagrams that we were showing you, that's exactly what happens. That is, if you sit at a fixed temperature and you increase the pressure and you're in the gas phase, then you will transition from a gas to a liquid or to a more condensed phase. So now the question we now want to do is to take these qualitative ideas that we've been describing and turn them into some sort of almost mathematical description of why materials have the phase behavior that they do. The reason that we want to do this is because we want to really try to put our fingers on the factors that are causing the different phase boundaries to be where they are. And for this, there are really two different ways of looking at the problem that scientists use and that are really quite powerful. So the first way that scientists use to try to understand what the phase behavior of a material is to basically say that what a material is doing at any point in the phase diagram, that is at any temperature and pressure, is it's minimizing what we call the free energy of the system. So there's some quantity that basically describes the system, and the system is trying to minimize it, and it's by minimizing this quantity that we find out what behavior the system has. An analogy to this is that if we were to take a hill, a very hilly valley, and we were to put a ball on the hill, the ball actually would roll down to the bottom of the hill. And so the position of the ball in that case would be given by the fact that it is located in equilibrium at the bottom of the hill. In the same way, scientists would say that a material actually minimizes the free energy. And one then has to basically construct a theory for the free energy, which it turns out contains two different parts. One depends on, and both of which relate to the factors that I've been describing. So one important factor is the sticking of the molecules to each other. This is what we call the internal energy. And the other is the factor that relates to the motion of the molecules. And this is something that we've talked about a little before, and we'll talk about again. And this is called the entropy. And entropy is basically the notion that the atoms in a material, to maximize their entropy, would like to be as far apart as they possibly can. They would like to be as free to move as possible. And it's this competition between the energy, that is the need to stick to each other, and on the other hand, the desire to be as free to move as possible, that leads to the different phase behaviors of materials. So that's the first way of looking at it. The second way of looking at it is more microscopic, and this is the perspective that we're going to take in more detail here, because we feel that it will give you more of a physical insight into what is actually going on that will be generalizable to more cooking materials. And in this, we simply focus on the behavior of a single molecule and say, well, what is happening to this molecule? And what's happening is that the molecule is sticking to others, and it's also moving. And so we're going to think about phase behavior as being the competition between, on one hand, sticking, because it wants to stick to the others around it, on the other hand, motion, because the molecule also wants to move. Now, to make this more quantitative, we have to be able to quantify both sticking and moving, or jiggling. Sometimes I call moving jiggling, because, it likes to jiggle. And so let's just start by trying to quantify the behavior of jiggling. And for this, I want to recall the equation that we introduced last week in the first week of the class. And this was the equation, Q is equal to mCp delta T, that related how much heat you had to put into a material in order for the temperature to rise by an amount delta T. And remember, we said that heat is an energy, that you could think of it as an energy. It has the units of energy, and the units tend to be that of joules. So what we sort of want now is some way of characterizing the energy of a single molecule. So whereas this formula basically gives you the energy of an entire hunk of stuff, we would like to know what the energy is of a single molecule. And you can almost look at this equation and say that I must be able to just interpret it this way. And indeed, this was an idea that was first had by a great physicist by the name of Ludwig Boltzmann in the late 19th century. And he invented a formula which basically says the thermal energy of a molecule is proportional to the temperature of the molecule when measured in units, which we call degrees Kelvin. So degrees Kelvin, you can actually measure temperature in degrees Kelvin by simply taking the Celsius temperature and adding 273 to it, just the number 273. And the significance of that actually is that in units of Kelvin, the temperature can never go below zero. That is, the coldest temperature there is 0 degrees Kelvin, which corresponds to minus 273 degrees Celsius. And that actually corresponds to the temperature at which the molecule doesn't move at all. It just remains stationary. This was Boltzmann's idea. So the thermal energy of a molecule is then given by C times Kb times the temperature measured in degrees Kelvin. Kb is a universal constant of nature that we've named the Boltzmann Constant after Boltzmann in his honor. And it has a value which is 1.38 times 10 to the minus 23 joules per Kelvin. C is a number that depends on atmospheric pressure. For the simple materials that we're talking about at 1 atmosphere, it turns out the number is about 3/2. And so in what follows, we're going to use the value 3/2. We're going to put an extra video on the website, which explains the physics of this number in a little bit more detail for those of you who want to go beyond this. But for now, let's just take the number to be 3/2. So now what I want to do is just to evaluate the thermal energy of a molecule. Let's see what it is, and let's see what it is at room temperature. So just for simplicity, I'm going to say that room temperature is 27 degrees Celsius. It's a bit hot right now where I'm standing. And so that turns out to be 300 degrees Kelvin. And if we then take this formula of Boltzmann, we multiply 3/2, that's C, times the Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin, and we then multiply it by 300, we get the thermal energy of a molecule. And it turns out that that number is about 6 times 10 to the minus 21 joules. That's what the number is. And it's a pretty small number, actually, 10 to the minus 21 joules. I mean, if I jump up and down, the energy that I'm spending is much more than that. And of course, the reason is that I'm made of many molecules. But the thermal motion of any molecule in my body, the claim is, since we're at this temperature, 27 degrees Celsius, it's about 10 to the minus 21 joules. So what does this mean for the phase behavior of a material? So in order to do that, we have to compare it to something. We have to compare the energy of the jiggling, of the motion of the molecule, to the energy of the sticking of the molecules, the potential energy of the sticking of the molecules in the solution. One way to think about this is the following. Imagine that you were in a room which had very sticky walls, and you were bouncing around the room with a lot of energy. I tend to have a lot of energy. And the question is would you end up sticking to the walls or not? And well, the answer to that is the question of whether or not you have more energy than the walls have sticking power. If they do, then you will not stick to the walls. If they don't, then you will stick to the walls. And that's exactly what happens to the molecules in our said liquid. So the molecule, when it's in the liquid, sticks to the other molecules. If its motion is strong enough that it can escape, then it will. Otherwise, it will stick. We can basically summarize these ideas on a phase diagram in a very simple way. What we say is that the molecules are in a condensed phase when their interaction energy, that is the energy of interaction that they have with the other molecules, is much bigger than the thermal energy, C Kb times T. When that's the case, they will be in a condensed phase. They will be stuck. On the other hand, when the interaction energy is much smaller than the thermal energy, when the thermal energy dominates, then the molecules will be free and you will have a gas. And in between these two extremes, that is the place where the phase transition from a liquid to a solid occurs. And that actually gives us the equation of the week for this week, which is U is equal to C times Kb times T. That's our equation of the week. Here, I will clap. So the reason that this is our equation of the week is because this, in a single equation, contains all of the physics that I've been talking about. It tells you when phase transitions occur between condensed and non-condensed phases. But now, in order to use it, we have to be able to actually, we have to quantify one more thing, which is the interaction energy in the molecules. And this, of course, depends on the materials. So some materials have high interaction energies. Our equation of the week would then say that that would have a high boiling point, whereas other materials are weak and have lower interaction energies, and those would have a lower boiling point, and so on and so forth. And so we would expect, going back to some of our previous examples, that ethanol, which boils at a lower temperature than water, is going to have weaker bonds than that of water. And indeed, that is going to turn out to be the case. It turns out that there are 4 different types of molecular interactions that are important in cooking. And they go from the weakest to the strongest. So the weakest bonds are given by what we call van der Waals interactions. Slightly stronger, but still pretty weak bonds are called hydrogen bonds. Those are what happen in water. Actually, van der Waals interactions are the dominant interactions in ethanol. The next strongest bonds are called electrostatic bonds, and the very strong bonds are called covalent bonds. Covalent bonds are so strong that you basically don't tend to break them when you're cooking. So these different bonds have different energies that are associated with them. The typical energy of van der Waals interactions is a couple, maybe say 2 times 10 to the minus 20 joules per molecule. That is, every molecule has about 10 to the minus 20 joules. Hydrogen bonds have about the same order of magnitude, a little bit higher number, maybe say 4 times 10 to the minus 20 joules per molecule. And electrostatic and covalent bonds have much higher energies. Covalent bonds have energies which are of order, say, 8 times 10 to the minus 19 joules per molecule, sort of more than a factor of 10 larger in energy. And these are the things that set the scale. You can see from this, and thinking about our equation of the week, that you immediately see that a material which has bonds that are covalent is going to actually melt or boil at a much higher temperature than those that are made of van der Waals interactions. And indeed, that is the case in the materials that we've described. I mean, actually, the reason that liquid nitrogen actually is a gas at room temperature is because it has bonds that are much weaker than those that are in ethanol and water. And that actually provides a framework for us to think about these various things. So I'd just like to summarize by explaining why I think this equation is so cool. So it summarizes all of the physics that we've discussed so far. It relates the motion of molecules and thus the temperature that you're imparting in the system with the interaction energies that the molecules feel with each other, and thus explains why different materials have different phase behaviors. So for example, if you have a material where the bonds are stronger, it will have a higher temperature at which it comes apart, boils or melts. If you have a material that you increase the pressure around it, then you're squeezing it together more and you're making it harder for it to come apart, which means that you have to heat it to higher temperature for this to occur. And these are, if you think through what we've talked about in these lectures, at the core of the structure of the phase diagrams that we've shown. Now, it doesn't apply, as I've stated it, for eggs or for complicated cooking materials, but what we're going to start to see in what goes forwards, that these basic principles, that is the competition between jiggling and sticking, the competition between energy and entropy, these are also at the heart of the transitions that occur in cooking materials as well. And in the next segment, we're going to talk about the melting of fats, which is slightly more complicated than what we've talked about thus far. And you will see that the same principles apply there. And then later on, we will start to talk about more complicated things. When you make cheese, for example, you heat up milk to a high temperature, causing the molecules within the milk to come apart and then to reaggregate when they're put under the right conditions. And it's that coming apart that's the competition again between the jiggling and sticking, or energy and entropy, if you will, which is at the heart of what we've discussed.